Problem number 2. Also, we started this in class, but I figured I'd go back through it again and finish it and get the answer for you guys. Clearly, if I'm talking too much and you want to fast forward to the next step, go for it. That's the beauty of recording lessons. Again, starting from the beginning and reading through the question for the essential information. In this problem, I do note right away, whoa, I don't want to do that. I do note right away that the largest possible area indicates to me the maximum for the area function. So maximizing area is going to be key. Then I might as well draw a picture that describes the rest of the problem. I have a right triangle whose hypotenuse is 5 centimeters long, and area for the dimensions of the triangle. So we were using base and height in class as our dimensions of the triangle. And the function that describes area is area equals 1/2 base times height. This again is going to be my derivative function, but because I have a b and an h, the goal is to make this in terms of just one variable prior to taking a derivative. So if I want just the base b value as my only variable, I need a secondary equation. I'm going to draw that in red from now on. The secondary equation that comes from the situation that allows me to solve for a variable and eliminate it from our problem. In this case, this is a hypotenuse of 5, gives us that Pythagorean theorem. And I can solve, I can eliminate h. So I can say that h is equal to 25 minus b squared under a square root. And that will be the substitution so that I can just have one variable down here. In one of our classes, we tried to simplify this. In the other one, we just took a straight derivative, which is what I'm going to do here. So taking the derivative of area, it looks like a product rule where I have two different parts of the product. So our derivative is 1/2 b times the derivative of the square root, which is 1/2 square root of 25 minus b squared, and the chain rule times the derivative of the inside, which is just -2b. Second part of the product rule plus the derivative of the first piece, which is 1/2, and leave the second part of the product alone. So there's our derivative. It looks kind of nasty. We know that we're supposed to try to get our derivative equal to 0. So as I rewrite this, I'm going to clean it up a little bit, and I can reduce a pair of those 2's, so I have -b squared over 2 root 25 minus b squared plus 1/2 root 25 minus b squared. Now setting that equal to 0, I see that because I have a sum, I can move that first term over to the other side of the equal sign, add it to both sides, and then I have a proportion, so I can do a cross product. It's probably the easiest way to solve this problem. So the cross product is, oh, and then when I do that cross product, that root goes away when I do a root, square root times a square root. And then continue to solve. This is a quadratic, so I want to set it equal to 0. I can also divide my 2's out at that point in time. And I have 25 minus b squared and subtract b squared on both sides. So I've got 25 minus 2b squared, which is going to allow me to, oh, I could do a square root. I can get this into a 2b squared equals 25, and solve for b squared by dividing by 2 and taking the square root of both sides. I should have a plus or minus on this technically, but in this case, if we refer to what we're measuring the base of a triangle. So you know, I'm going to now erase it off. I don't need the negative because we don't have a negative side for a base here. So just really the positive square root. And then I can simplify that. You know, if you really want to go into all the details of simplifying, this would be, I can't have a radical in the denominator. So I'd have a 5 root 2 over 2 as my b value. Now that's the critical value. That's the value that shows us where we have a critical value of the derivative from setting the derivative equal to 0. This was a longer derivative and also a longer solving, but it's going to be fairly quick now to take that value and test it. So I'm going to go back up to the top here and test 5 root 2 over 2 in a first derivative test. So a prime, or b value, is 5 root 2 over 2. Not too sure what that is, but it's good to look right now and see what we have as a, that's weird, what we have as a value for domain. Now the domain on this case is that this is the base. We talked about this a little in class, and the base has to be bigger than nothing, and it can't be bigger than 5 if the whole hypotenuse was flat on the ground. That allows me to test some numbers. I might test a number that's, you know, really close to 0 in my derivative test. So let's go down here to 1 and then up here to 4. Those are probably on either side of 5 root 2 over 2. So back in the derivative. Now where's the easiest derivative to look at? Maybe this one right here, this form of the derivative for testing. So if I test a 1, I have a negative in the numerator. And then in the denominator, all of our square roots are going to be positive. So the entire denominator will be a positive number. And then I'm adding on 1/2 times a square root, which is also going to be a positive number. This is ending up to be not quite as easy as I wanted. I might have to go and actually find a value here. So I'm going to do a little bit more work. Instead of that negative analysis, positive analysis. 2, and that, if I plug a 1 into the b value, that's going to be 25 minus 1, or square root of 24, plus 1/2 square root of 24. Now, I don't know. Can I analyze that and just say if it's positive or negative? Might want to pick up my calculator. You might want to justify what I'm doing with the calculator here, but I'm going to look at that first term and say it's a negative fraction. And the second term is a positive non-fraction bigger than 1. So I'm going to say that if I do this in my head, it's going to be a positive number. Should probably validate that this is true on the calculator. If we plug in a 4, so that's going to be the other side of our critical value, I'd have a negative 16 over 2 times the square root of 1. This one's a lot easier. And then plus 1/2 square root of 1. Now that is, to me, clearly a negative 8 plus 1/2, definitely a negative value up there. So just like the prior problem, we actually have a increasing to decreasing, and so this critical value is a max, which is nice because that's what we wanted to do. We wanted to maximize our area. All right, so we've confirmed that the b value of 5 root 2 over 2. We should probably find the h value that goes with this, because we have to answer the question up above. Look at this question. It says, what are the dimensions of the triangle? So I have one of the dimensions, and I need to find the second dimension, h. Now, oh, that comes back right up from the substitution equation back here again. So if I plug in 5 root 2 over 2, which is actually, I saw it earlier as the square root of 25 over 2 squared. Let me do a little bit of work here. This is an earlier version of b that I'm using. So this is coming out to be 25 minus 25 halves. That's 50 halves minus 25 halves, it's also 25 over 2. So the height, the base and the height both in this situation are 5 root 2 over 2. So those dimensions maximize the triangle. Oh, the triangle's area. And then, you know, does that make sense? It could. It could certainly make sense if we think about this as a right triangle. And if the legs of the right triangle are equal, and it's an isosceles right triangle, that is going to have a bigger area than a tall or a short right triangle would. So that does kind of make sense that that's a maximum area for that triangle, the isosceles version. All right, on to number 3.